Okay, so let's take a look here at one more example here with the related rates. This time we're told that a boat is being towed into the dock by a winch. Uh, the winch is positioned 10 feet above the level of the boat, and we know that the winch is winding in the line that's connected to the boat at a constant rate of 1.5 feet per second. And we know that the winch is winding it in at a constant rate. So the winch is turning around at a constant rate, pulling in the rope as well. So our question is, how fast is the boat moving when it's 25 feet away? So very key here. Let's take our information and make a picture here. So here I'm going to draw in my water level down here. Water level. Here's my dock up here. And we have a boat down here in the water, right? And we're pulling that towards the dock. And we are 10 feet at a point 10 feet above the water level. Okay, so that's our picture. Let's think first of all about quantities that can change. So first of all, the distance between the boat and the dock, that can change, so let's call that x. Now the winch is always 10 feet above the water level, okay, 10 feet above the boat level. So that's not ever going to change. But the distance, the amount of rope between the winch and the boat, that's going to change as we wind it in. So this is our visual picture here, and of course, this is a right triangle here. Right, this is a right triangle, right, because the boat's straight up from the water level, or the dock straight up from the water level. So we need to find a relationship between x and h, but let's also keep in mind what we know. So we know that the rope is being wound in at a rate of 1.5 feet per second. So that tells us the HDT is a negative 1.5. It's getting shorter. We want to know how fast the boat's moving at. So in our picture, we know the boat is currently 25 feet away. We want to find dxdt, right? We want to find dxdt. How fast is the boat moving? So what we can say is this. Looks like I undid something here. There, fix that up. X squared plus 100, 10 squared, right? Pythagorean theorem again, equals h squared. So that's the relationship between x and h. And we will probably eventually need to use that to figure out what h is when we get into our problem here. But for now, we can go ahead and differentiate that equation to get the relationship between dx dt and dh dt. So derivative of x squared would be 2x dx dt. Derivative of 100 is 0. Derivative of h squared would be 2h dh dt. And so you can see we're looking for dx dt. We know dh dt, that's negative 1.5. But we're looking for dx dt. So we're going to have to divide both sides by 2x to get dx dt by itself. So we're going to get 2h over 2x, so the 2's cancel out. We just get h over x dh dt. H over x dh dt. So you see, yeah, we do need to know what h is. We do need to know what h is. So we go back and we put that information into our equation. X is 25, so 25 squared plus 100 is going to be equal to h squared. 25 squared is 625, plus 100 is 725, and if you simplify square root of 725, because that's what we're going to have to do to get h, right? H squared is equal to 725, so we take square root, you get square root of 725, that will simplify to be 5 square roots of 29. Again, we're going to be looking for a decimal answer here, so if you kept that as square root of 725, unless the problem wanted an exact answer, leaving it at a square root of 725 would not really hurt. So let's put our information in now. H is 5 square roots of 29, or square root of 725. Divide it by 25, and that's times the h dt, which is a negative 1.5. And then we just simplify. And we get that the boat is currently moving at a rate of about 1.62 feet per second. So it's moving a little bit faster. It's moving a little bit faster than the ropes being pulled in at. A little bit faster than the ropes being pulled in at. And that's coming from that fraction h over x, because the h dt is constant. So one of the things I want you to notice here is as you get really, really close to the dock, as x gets close, very small, the x dt rate's going to like explode. Right? If x is 1 foot away from the dock, you still have about 10 feet of rope. So the boat's going to be moving extremely fast. So you actually have to let off on that winch. There's another issue as well. When you get really close, a large amount of the pole is being occupied by that 10 feet. It's trying to lift the boat off. And that's not going to happen. It's not going to pull the boat up out of the water. So your winch is naturally going to need to slow down. It's not going to have enough power because it's trying to, a large part of, if you have 1 foot and 10 feet, a large part of that pole, on that 11 feet of rope is trying to yank the boat off the water, which really isn't going to happen. So, but as you get close, x is getting very small. The x dt would actually explode and get really big. So you have to actually let off on the winch once you have the boat coming in, so that it kind of comes in slowly. All right, you have to pull it in for a little while, but it's going to keep picking up speed, and so eventually you're going to have to let off. So otherwise, you're going to have some problems. You're going to need to build a new dock. Okay. So hopefully it helps you here as you're working these related rate problems. Again, they're tough, but you need to come up with a relationship, differentiate it. That process is kind of the same in all of them. Okay, till next time.